during the course of interchanging the position of any two electrons. Okay, so definitely, okay, there will be always, it will be 1 and the opposite sign will be present, isn't it? Okay, if it is a symmetric means that arrow will be, 2 arrow will be in the upward, or 2 arrow will be downward. But during the course of during the course of studying the overall wave functions, always in orbit, 1 electron and 2 electron means definitely it will be in a antisymmetry. It won't be in a symmetry. Okay, so in an orbit. Okay, so here the probability is symmetric or antisymmetric. That is, if it does not change the sign on interchanging the position of any two electrons, or it may be antisymmetric. That is, if it changes the sign on interchange of any interchange of position of any two electrons. So among the several linear combination of the product functions, we have to choose linear combinations which is only antisymmetric with respect to interchange of position of any two electrons as our overall wave functions for many electron systems. Okay, so we have to ignore the symmetric systems and we have to look into the things, whatever antisymmetric is should be the overall wave functions in the case of many electron systems. So here, if you talk about the many electron systems, first, in order to minimize the complexity, we'll choose starting from the helium atoms, that is 2 electron systems. And here the 2 electrons means it is a kind of a 2 factorial, that is a 2 into 1 product wave functions may be present. And it can be given as either pi of 1 of 1 into pi of 1 of pi of 2 of 2, or we can say, okay, in orbit, it has a 2 orbit. Okay, so the electron may be present in, okay, electron 1 and 2 may be present, or electron 2 and 1 can be present. So we don't know, because it is a indistinguishable kind of things. So there are 2 linear combinations may be present. Okay, so either with respect to, okay, so here the overall wave functions should be normalized. So in order to find the normalized wave functions, here we have to take that wave functions with respect to symmetric wave functions and antisymmetric wave functions. That is n of pi of 1 of 1 plus into pi of 2 of 2 plus pi of 1 of 2 into pi of 2 of 1. The bracket 1 and 2 says the electron 1 and 2. Okay, the mix, and we have to take only the psi minus as a overall wave function, even though it has both the psi plus and psi minus, and we have to take only the psi minus. The reason is it is only the antisymmetric with respect to each other. Okay, so right, for every wave functions we have to find out the normalization constant, isn't it? So in the both in all the particle in a box and everywhere, the normalization constant should be calculated. So likewise here, the normalization of the wave function should be achieved for this antisymmetric wave functions. So just take the normalization condition is always okay, integration of psi square into dou dou t1 into dou t2 is equal to 1. That is called as a condition for the normalizations. I think from the particle in a box you used to study these things. So fix the value of psi value within this content means. So it says the constant, put it outside, and thereby, okay, so here we can check it out like a minus b whole square formula, and using that formula we can find out the value of normalization constant value, or n value is calculated, and the n value is calculated as 1 by root of 2. Okay, so that is the values is calculated. So the normalized wave functions for 2 electron system is obviously, okay, so the wave functions can be written in a kind of a determinant form. That is, if it is only 2 electron is present, you have to give it in that, just like in a matrix methodology, that is pi of 1, pi of 2. Okay, okay. If there is a 2 electron is present, and the possibility is, okay, so it is either in any one of the orbit may be present. So it may be in pi 1 system or in pi 2 systems. The first electron will be present. Likewise, the second electron may be present in either in pi 1 or in pi 2. Okay, so this is called as determinant wave functions or Slater determinants. So the normalization constant can be varied with respect to the number of electrons. Okay, many electron systems case, if it is a 2 electron means it says that 2 factorial or 2 factorial values is present, and the normalization value is 1 by root 2. Whereas in the case of 3 electron means it is a 3 factorial, that is a 3 into 2, that is a 6 case, thereby it is called as 1 by root of 6. And if it is a 4 electron systems, it is 4 into 3 into 2, that is 4 3s are 12, and 12 into 2 24. So thereby 1 by 20 root of 24, or you can give it as 1 by root 2 factorial, or 1 by root 3 factorial, or 1 by root 4 factorial, all are same. Okay, either 1 by root 2 or 1 by root 6 or 1 by root 24 or 1 by root 2 factorial or 3 factorial or 4 factorial. Okay, for an electron system means the number of product function is n factorial, and thereby the normalization constant is given as 1 by root of n factorial. Okay, so the normalized wave function for 2 electrons is given here. Similarly, if it is a kind of n electron means you have to give the, okay, so the normalized wave functions like okay, so like a matrix methodology, that is keep the normalization constant outside, that is a 1 by root of n factorial into, okay, how many electrons is present. If it is a 2 electrons or 3 electrons or n electrons, accordingly you have to give the normalized wave functions. So this form of wave function is called as a Slater determinants or determinantal wave functions, and it should satisfy the antisymmetric requirement to the Pauli's exclusion principles. That is very important. So that is by conventions, while writing the determinantal wave functions, normally we used to take the diagonal elements. Okay, that is very important, and in order to minimize the complexity, so we can take it, if it is only 2 electron means we have to take that pi of 1 into pi of 2 of 2. Okay, likewise if it is a many electron means accordingly we have to choose it by means of the diagonal elements, and each orbital can accommodate only 2 electrons, one with alpha spin and the other one is with beta spin, isn't it? Okay, so the above wave functions can be written, okay, in terms of with respect to, okay, 1 electron with alpha spin and beta spin, thereby pi of 1 into pi of symmetric and antisymmetric values, and likewise either the second electron also with respect to either symmetric or antisymmetric. Okay, alpha spin or in a beta spin. Okay, so that is the spin orbital pi of 1 occupied by the electron 1 with the alpha spin. Okay, and also there is a possibility with respect to the beta spin. Okay, so thereby there is a possibilities. Okay, probability will be enhanced. So this kind of expansion, so you can stop it. That is the diagonal element may be taken out, and there you can stop in terms of Slater determinants. So most of the competitive exams are in your semester examinations. Definitely, the determinantal wave functions are, they may ask about what do you mean by Slater determinants, or how it satisfies the Pauli's exclusion principle, and those kind of topics may be asked. Okay, so or simply you can write how to write the Slater determinants for 2 electron systems or 3 electron systems. It's very easy. So only thing is just like a formula. Okay, if it is a helium atoms, you have to take like wave functions with respect to 1 of 2, 1 comma 2, and 1 by 2 factorial can be given, or 1 by 2 can be taken. Similarly, if it is a 3 electron system means there is a, okay, so 3 atomic orbitals and 3 electron is present, and thereby the wave function should be taken in psi of 1, 2, 3, isn't it? And thereby you have to take 1 by 3 factorial, or 3 into 2, 1 by root of 6, whatever it may be. And here the 3 electrons means the 3 electrons can be accommodated in any one of the orbit, like pi 1, pi 2, or pi 3. So here 3 into 3 kind of matrix you have to give. In the earlier case, in the case of helium atom, we have drawn 2 into 2 matrix. Since it is a 3 electron system, so it is a 3 into 3 matrix. Likewise, if it is a kind of beryllium or boron or carbon, so how many electron is present over there? Accordingly, okay, you have to say in the case of 6 electron, in the case of carbon, obviously you have to give it as 1 by 6 factorial into 6 into 6 matrix should be given. Likewise, in the case of boron, it is a kind of a 5 into 5 matrix, etc. Or in the case of beryllium, 4 into 4 matrix should be drawn. So it is very easy. Only thing is how to write these things, and by taking into the account of in terms of both the electronic spin